Can you see my screen?
Yes.
Yes,
Okay,
yes,
thank
yes, very
you
nice.
so much. First of all, I would like to thank the organizers for giving me the opportunity to present our work in this nice conference. Thank you very much. Our work entitled Detection of Buried Chiral Objects Using Electromagnetic Scattering in Two Dimensions. This is a joint work with Spiridon Athanasiadis. The outline of the talk. First of all, we will start describing the mean of chirality, a property that chiral obstacles have, and then we will briefly see some applications in which the detection of chiral objects is necessary. In fact, the detection is based on solving an inverse scattering problem. So, we will formulate this problem. First of all, we will start with three-dimensional case, and then we are going to reduce it to a two-dimensional case. The reason that we need to formulate the problem in two dimensions is that it is very easier to solve it, and then we can obtain an approximation of the corresponding three-dimensional problem in which we want to estimate the solution. In order to do this, we are going to use the reciprocity gap functional, which is modified in order to work in chiral media. We will end this presentation with some concluding remarks. Okay, let us now start with a few words about chiral media. Chiral materials are those which exhibit the phenomenon of optical activity. The term chiral comes from the Greek word hand and was first introduced by Lord Kelvin in 1904. Chirality is a geometric property related to the lack of structure symmetry of a body. It appears in mathematics, biology, chemistry, and physics. As we can see in this figure, we can see the optical property of chiral materials. It's like our hand. Okay, and now some chiral structures that appear in real-world problems are DNA helix, snails, flowers, and crystals. For example, if crystals are buried in the ground, we can solve an inverse scattering problem in order to find them. Many scientific applications in which we need to detect objects are geology, biomedicine, and telecommunications. The basic idea of detecting buried obstacles is based on solving an inverse scattering problem of wave fields. In particular, we have acoustic waves, electromagnetic waves, and elastic waves. As we can see in this figure, we have a source which derives waves. These waves are incident to our object, which is buried here, and these incident waves are produced scattered fields. The wave is scattered by the object, and we have to measure the scattered field. And then we know the incident and the scattered fields, and we can apply a method of solving inverse scattering problems in order to determine the physical properties and the shape of this buried obstacle. There are a lot of methods in order to solve inverse scattering problems, but the classical methods cannot be easily applied in order to detect the buried obstacles in ground. This is due to the fact that The difficulty of distinguishing the scattered field due to the target from the scattered fields due to the ground, the antenna, etc. And another reason is that the material properties of the target are in general unknown. The linear sampling method overcomes these difficulties. However, this method requires the knowledge of the Green's function for the background media. A new version of the linear sampling method based on the reciprocity gap functional was introduced by Colton and Hadar in 2005 for the scalar case and by Cacconi, Fers, and Hadar in 2006 for the vector case. This method, which is based on the reciprocity gap functional, has not to compute the Green's function of the background material, and this is a great advantage of this method. So, in the present work, we are going to describe this reciprocity gap functional method in order to solve an inverse scattering problem. Let us now start with the formulation of the problem in 3 dimensions. First of all, we consider d tilde a bound in the region with a S2 boundary. This region is occupied by homogeneous isotropic chiral medium, which has chirality measure β, electric permittivity epsilon, and magnetic permeability μ. The exterior of the scatterer is an achiral infinite free space, which has electric permittivity epsilon 0 and magnetic permeability μ0. As we can see in this figure, we have the scatterer in 3 dimensions. We denote the scatter by d tilde. The basic constants of this scatterer are epsilon, μ, and β, and S is the boundary of the scatterer. In this scatterer, we have incident fields, electromagnetic fields, E incident and H incident, which are going to the scatterer, and then we have the corresponding scatter field. The total exterior electric field and the total exterior magnetic field satisfy the time harmonic Maxwell equations, which are given here and are held in R3 minus d tilde bar, where omega is the angular frequency. We consider that the incident electromagnetic wave is plane, and it is given by this formula here, which depend on kappa 0, which is the wave number, P, which is the polarization vector, and d hat, which is a unit vector and denotes the incident direction. The total exterior electromagnetic field is given by this summation. In fact, is the summation of the corresponding incident field and the corresponding scattered field. The scattered electromagnetic field satisfies the Silver-Miller radiation condition of this form. As we can see, we have this limit, R tends to infinity, and the result is equal to 0. This condition holds in all directions, x hat. In this figure, we can see the basic idea of the scattering problem. In particular, we have this scatterer, D. We have the boundary of D, which is denoted by S. We have the incident fields, which are going to the scatterer, and then they are scattering to ES and HS. Concerning our buried obstacle, which is a chiral object, we utilize the Drude-Born-Fedorov constitutive relations, which are given by this formula, where E is the electric field, H the magnetic field, D the electric displacement, and B the magnetic induction. More details about these relations and in general for chiral obstacles we can find in this book of Λαχτάκια. Then, suppressing a time dependence and using the source-free Maxwell-Chiral postulates and the constitutive relations, the electric and the magnetic fields satisfy these equations. In fact, as we can see, this is the modified Maxwell equations, which depend on gamma squared, which is equal to this quantity. We assume that all the fields are divergence-free. And concerning our transmission conditions for a dielectric, we consider these two transmission conditions which are imposed on the total fields on the boundary of our scatterer. But as I have mentioned in the introduction of our talk, in order to solve the three-dimensional problem, it is a hard problem. So we can reduce the corresponding three-dimensional problem to another easier problem in 2 dimensions. We can solve the easier problem and then we can derive an approximation of the corresponding three-dimensional problem. In order to do this, we have to consider that d tilde is an infinitely long cylinder which is oriented parallel to the x3 axis. D is the cross-section of d tilde in the x1, x2 plane with a Z2, Z2 boundary, and omega is a bounded domain which contains D. dB is the background medium with electric permittivity epsilon B and magnetic permeability μB. In this figure, we can see the two-dimensional scatterer. As we can see, we have here the scatterer D with constants epsilon, μ, and chirality beta. The boundary of the scatterer is denoted by S, and here dB denotes the corresponding background. In our case, maybe is the ground, the earth that is embedded the scatterer. And D0 is the outside of the ground and the scatterer. In order to formulate our problem in 2 dimensions, we have to assume that all the fields are independent of the Chytria variable. And moreover, we have to assume that the incident and the scattered outside waves are given by this form, and the corresponding total electromagnetic wave is given by this form. We have supposed these forms of these fields following this book of Cacconi and Colton, in which they have imposed these basic assumptions in order to reduce a three-dimensional problem to the corresponding two-dimensional. By using these assumptions, it is easy to see that the total electric field is given by this form, and by using the Maxwell equations, we can obtain that the total magnetic field is given by this form. Then, the total field U we can write a compact formula for the three spaces that we are interested in studying our problem. The compact formula is given here, and it is, in fact, a Helmholtz equation with a corresponding wave number, as we can see in this slide, where n of x is equal to this formula, and this formula depends on the space that we are in. Next, we assume that the incident field is a spherical two-dimensional wave, and it is given here, which in fact is a fundamental solution of the Helmholtz equation, which is given by this formula, which is depend on the Hankel function of zero order, and it is of first kind. The point source is located at x0, which belongs to a set lambda, where lambda is an auxiliary closed curve surrounding omega. Then, if we consider the initial figure that we have seen, the incident wave, which is denoted as U incident, which depends on the point source x0, is going to the scatterer. First, is passing from the ground, so we have this initial incident field, and we have this field, which is the position with the corresponding scatter field, which is scattered by the background medium. So the incident field on the scatterer is the superposition of the two fields. The scattered field satisfies the Sommerfeld radiation condition, which is given by this formula. And now, if we summarize the above analysis, we can formulate a two-dimensional scattering problem, as we can see in this slide, which is consists of the equations, the Helmholtz equation, which is held in D0, the outside of the scatterer and our background, and it holds also in the space of our background, and the Helmholtz equation, which is valid in our scatterer. We have the transmission conditions on the surface of our scatterer, and of course the Sommerfeld radiation condition. This problem is well posed, and so we can proceed in order to solve it. The last part of our talk is the reciprocity gap functional. First of all, we have to define the set H omega, which is the set of the solutions of this Helmholtz equation. Then we are in position to define the reciprocity gap functional, which is given by this formula, and this is the integral on a boundary omega, where U is the solution of the scattering problem for all x0 which are in lambda, and V is a function in H omega. This functional can be viewed as an operator, as we can see by this formula, given by this integral equation. In order to formulate our basic theorem, we have to consider this interior transmission problem. We have two Helmholtz equations which are valid in D, and we have these two transmission conditions. the eigenvalues of the corresponding homogeneous problem are the eigenvalues for D. If K0 is not an eigenvalue of D, then the operator R, we have proved that is injective and it has dense range. A subset of H omega, which will be used for the determination of the boundary of our buried obstacle D, is the set of Herlot's wave functions, which are given by this integral. These functions are solutions of the Helmholtz equation. The kernel of these Herlotz wave functions is denoted by G and is a function which is in L2 0 to 2p. The reciprocity gap functional method is to find an approximate solution G to this functional for Z, which is close to the boundary. And now we will state this theorem, which theorem allows us to define the boundary of our scatterer, and as a result, we can determine the buried obstacle. In particular, we assume that K0 is not an eigenvalue for D. Then, for Z in our scatterer D and epsilon a positive number, there exists a function G which depends on Z and epsilon, such that this norm is less than epsilon. What means that the Herlotz wave function converges to the solution of the interior boundary value problem in L2. For a fixed epsilon, we can get that as the distance of Z to the boundary D tends to 0, we have this norm tends to infinity, as well as this norm. And if we consider Z, which is outside the scatterer, we have that this norm of this functional minus this functional, which is an approximation of our desired functional, is less than epsilon. And then we have that the corresponding limits, as Z is close to the boundary, the corresponding norm tends to infinity. And some concluding remarks. First of all, we analyzed a two-dimensional scattering problem in chiral media. We described the method of the reciprocity gap functional in order to solve the inverse scattering problem and especially to determine the shape of the scatterer. Concerning our future work, we aim to develop the reciprocity gap functional method in case that the scatterer is embedded in chiral environment. And we aim to apply this method to real-world problems. Some more references concerning our work can be found in these slides. So, thank you very much for your attention.
Thank you, Professor Rupa. Very nice your presentations. Have got any questions, please? Well, I have a question. This is
Let me do
yes.
the question. Well, thank you for your report. It's really interesting, and with maybe strong mathematical basis for such kind of kind of research. But the question is, this kind of analysis is looks like the well-known type of tomography, two-dimensional tomography, based on the maybe gradational or different types of used points. And the question is, can be this result applied to not expected area of research, for example, map it directly to another environment, to maybe another materials with the usage of the same mathematical basis?
Thank you for the question. In fact, this period of time, we tried to find more applications in order to apply this method, but probably yes. We think that it is possible to apply this method in tomography and other applications.
Okay, thank you.
Thank you for question, for answer. Professor Rupa, tell me please, we see all the mathematics, all the background mathematics on this transformation, but have you made any simulations on that?
Oh.
How you make a proposal from the side of our sciences? How is working on that? How quick you can make all these transformations and all the computations?
In fact, we started to study this problem in 3 dimensions, and we have seen that it is difficult, as we mentioned in the presentation, to simulate this method. And then we proceed in 2-dimensional. And this period of time, we are working on deriving simulations, yes, in 2 dimensions. But for the first, from the first results, we see that it is promising.
Yes, thank you, because it's very important as you make the 2-dimensional, 3-dimensional, say here, when we turn around all that, is like the systems that we need to find to make the identification of objects behind us or anything about that. Not only in tomography, it's very small, but also in a big objects that they run quickly, like airplanes or anything, or which is running when they have to be on crash and they have to avoid something, and etc. So recognition and the single process is very interesting for us. So look for future work on that to make simulations and the special. I think with the work of Artyom that we see before, it's very important if we can do it with FPGA's level, hardware level. Well, thank you very much. Any more questions? No more questions. Thank you very much. Thank you very much. Let's see if any of our presenters here, they could connect Professor Devance or